We're in Japan, we're in Korea, we're in the UK, we're in Ireland, we're in the Netherlands, we're in New York, California, Colorado, Arizona. So we travel a lot. I travel a lot. United Airlines loves me. My wife, not so much. So, you know, I'm only staying here for the day. All right, now, I often don't talk about the business of space, and I was told that this would probably be a better venue here to talk to you about how do you get into this business on space and sciences. How do you run it? If you want to run your own company, how do you be that entrepreneur, and what kind of guidance I could give you. So, I stole that picture. I certainly didn't make it. This is part of it. You have to be smart. You have to be extremely smart. If you're going to start a company yourself, you need to surround yourself with even smarter people than you. I used to, my goal at the Broad Reach Engineering when I started it was I wanted to be the dumbest one in the company. I ended up hiring 60-something people, and I know I failed in that 4 times. So my dumb friends and I, we get together and help work with all the smart guys. Somebody told me something similar. This A people hire A+ people. This guy, Kawasaki, I have not read his book, but I wanted to put that little footnote because apparently our Rand Paul was getting all trouble because he wasn't referencing the things that he was saying. But I would also say that every single word I say, I'm sure somebody else had said it at a previous time someplace. But anyway, you need to hire talent in everything that you do, whether it's science or engineering, law, contract management, IT, you IT guys. So I want to make sure that if you do start a company and you have an idea, that idea needs support around it. It needs execution, it needs finances, it needs time and efforts. So I just want to make sure that if you ever do start, get advice. When I started my company, the first thing I did was go down to the Small Business Administration to say, hey, I'm an aerospace engineer. How hard can it be to run a company? Well, you don't know what you don't know. So it's not always easy, but in the aggregate, it's always fun. So I encourage you guys to start your own companies if you want to. It's too hard to start in this industry by yourself unless you go ahead and get 2 years experience, 10 years experience, whatever it is, just to see who the movers and shakers are and who the players are. Because you just don't, here's a product and then somebody buys it. It doesn't really happen that way at least the science industry. The other one is be relevant. You really need to work on your particular talents of what you're trying to get done, why you're even in the business. So when I do talk to people about trying to be a part of the science itself, be the reason why you're flying. Why are we spending these tens and hundreds of millions of dollars for rockets and spacecraft and payloads? What are we trying to bring back, and what kind of attributes? So you want to always know what you're trying to do in the end game, although you might just be making a reaction wheel. You're writing some lines of code, you're designing the orbits, you're doing whatever they are. It's a piece of a huge big picture of trying to capture the knowledge and science we want. So be relevant in what you as a company person, or you as a part of Lockheed Martin or Moog or anything else. Know that position. The other big thing is science is a trust business. And this is one thing I've been talking to a lot of the Moog sales guys. Once you start getting in the science realm, you might spend years talking to principal investigators and scientists and say, what are we really trying to do? You get their trust. You never talk about schedule or money. You're trying. What are you trying to do? And can I trust you to be there with me for the next 2 years, or next 5 years, or next 20 years? Because the execution of science takes generally large fractions of decades. The other thing that are kind of saying that there's the movers and shakers, there's really only hundreds of them. They're not hundreds of thousands. When you go out there on who's really controlling what missions, and some of them are based here at different universities, at University of Arizona, or ASU, or University of Colorado, the Laboratory for Atmospheric Space Physics that ran the Kepler mission. They were the controllers of that. It's very, most of these science instruments and science missions are very, very noble pursuits. Kepler, we're saying that, okay, well, they think there's 40 billion potential Earth types of planets in just this galaxy. And how many galaxies are there? Well, we don't really know. So having the knowledge base of instruments that are that fine and that ability to design things over those many decades, and how much smarter than we are than your parents or my parents or my great-grandparents. They couldn't even imagine what we're trying to do right now in terms of the science realm. So whatever the science that you guys get involved in 10 years from now, you'll think, Kepler's old hat. You've got another 2 orders of magnitude better resolution. You've got better knowledge of really where to look on aspects. So a lot of it was, how do you get involved? And if you lose the trust, you're out. It's a broken glass. So it's okay to fail, but it's not okay to take advantage of anybody, anything. The next one is just for context on the types of industry or types of parts of this industry. One is industry and one is science. And the industry side is kind of broken down. I got another chart about it. Commercial payloads. Necessarily know if we need more art. How our story. So if you're going to run a company in almost anything, especially in the development side, you need to know that answer. Quit focusing on money. Money's a tool. You need lots of it. But you really need to know why you're making something and how does it fit in the industry, because there's not that many buyers. The other big thing was look at a mission requirement as a mission requirement. My example is there, hey, the mission requirement is bring back 1 kilogram, which is for you non-engineers, 2.201 pounds of stuff back from Mars. That's the requirement. Not all these other derived requirements that Orbital Sciences or Moog or Lockheed or JPL tells you. Those are derived requirements, and those are choices people make. The other thing is that last bullet is really true. You have a lot more training in some ways in school than we did. I don't do anything I ever learned in school anymore, and I didn't after about 10 years after I got out of school, except for orbits. I still do orbits. Kepler, Newton, those are kind of old stuff, but more orbit perturbations. The gravity field is kind of funny. The Earth is a little lumpy in the middle. For you aerospace guys, you'll know that the Earth is oblate. It's not a sphere. It's got a beer gut. It's all those Irish bars, I guess. But yeah, you can and you will be smarter than your boss in some of the topics. We do have the benefit of experience. I've been fortunate enough to be involved in dozens of different space missions, and most of them experiments or science. A lot of serial number ones. The other thing about the uniqueness of space is, on the science side, you are often only building one. So you don't have a statistical sample. You're building one. It's all hand-built. It's a piece of art. It's got to work. And I think that's great. Instead of, oh, well, I built 100,000 of, this car or this wheel or this tire. No, we landed stuff on Mars and we got this much data returned. I think that's much more exciting for me personally. I already kind of mentioned that it's really a trust business. Launch vehicles really only need to last 8 to 15 minutes. And where I'm putting this up in a time scale, certainly it takes years and years and years to develop a launch vehicle. But from the emotional content of what people do, and I'm going to pick on Dr. McLeese a little bit. He built this PIMR, this pulse modulated infrared radiometer. It was an instrument specifically designed, a weather instrument for Mars. He spent a better part of 2 decades getting the ability to get on a spacecraft going to Mars, Mars Observer. So Mars Observer was this old RCA kind of geo bus that said, okay, well, these satellites are made to go around Earth. We'll just send it to go around Mars, and we'll put all these payloads on. So it gets already to Mars, and it blows up. I said, well, this instrument is so valuable. Let's go ahead and put it on the next one we can. And he can't. It's all hand built. He can't build one fast enough to get on the Mars Global Surveyor mission, but he'll get on the next one, the Mars 98 mission. So he builds this whole thing, gets on the Mars 98 mission, goes all the way to Mars, and splats right into Mars. And that's been another 10 years. So he's got 25 to 30 years of his career in this instrument, and he gets to Mars twice and goes splat. He's got a huge emotional investment. The people who built on those spacecraft, they spend 2, 3, 4, 5 years designing the spacecraft to host all these payloads to actually accomplish these kind of missions. So they got a lot of time and effort into it. Now the launch vehicles people, whenever they have a failure or a problem or something, it goes up halfway up and blows up. The launch people say, oh crap, I'm not going to be able to launch for another 6 months. All these problem reports trying to find what's wrong and everything else. And then they're back in business 6 months later. The people like Dan McLeese, he's got his career tied up into systems that failed. So his ability to internalize what he's doing is much more difficult. And he's a great man. I think he's still at JPL. But when you do get into the launch vehicle people, they are, hey, it's a big rocket. It's going to last generally 12 to 15 minutes, and that's it. That's all it has to last. It has to be excellent for 12 to 15 minutes and put you where you need to put. But everybody else has to last for 15 years. So the time scales of how you design something robustly are totally different. Now, for your MBAs and your econ majors in the room, I did make this comment that I did have this term EBITDA, schmebida on it. Because a lot of guys were talking about, oh, what's your earnings before interest, taxes, depreciation, and amortization of all your tools? And people would ask me that even when I was running Broadreach Engineering. And I said, well, I don't care. Well, you have to care. You have to know how well you're doing. What's your profits, all that kind of stuff. So no, I'm making a difference. Getting to know your EBITDA is something that certainly public trading companies have to do every quarter, because we're filing every quarter. Moog has to do that every quarter. But from a small business perspective, it's like you owning a house, and every month you're paying $400 to see how much your house is worth. You don't care. It's not information that you really care about. You really care about survival. And I tried to do this econ equation on survival and say, hey, you need to make sure that your checks don't bounce. In the aggregate, you better have more money coming in than going out, and that you have this generally a line of credit at the bank as a capacitor to make sure your accounts receivable, accounts payable eventually even up. So when you guys start companies 2 years from now or 10 years from now or something, don't focus on profits. Profits are derived value. You focus on survival, and you focus on being relevant. What are the products that you have? Why do people want it even if it's free? And then go make money on it too. The other part of what I was getting after my MBA friends is, what do you learn and what do you don't learn when you're running a small business? And a lot of it was, they said, well, you're in the business to make money. And I would politely say, bullshit. We're not a printing press. We're in the business of creation. We're in the business of making a difference, especially on the science side of stuff. It's very ennobling to be able to make our brains bigger somehow, just be a part of that. And I'd say, hey, money is a tool. It's good to have lots of tools. That's not a problem. But if you're focused on money, don't go into this industry. I mean, certainly you can make money. You can make a lot of money. But if you're only focused on money, it's, go be a Wall Street trader or something. I have no patience for that. I mean, I think it's great being human that we want our brains bigger. So that's what I'm more focused on. The other one was back to the business of science. Like I said, I'm personally much more involved in trying to make this industry better for all of us on the knowledge and science side. The other big thing that I was a huge proponent of at Broadreach Engineering, I was making sure all the engineers there owned a part of the company. And even at Moog, I'm buying stock at Moog because I believe in what I do. I think you need to own a part of what you do, whether you work at Lockheed or Moog or a startup company. Make sure you own stock, not stock options, not all that kind of crap that people could get, that other people get screw you on, basically. And sometimes they will, because not everybody's trustworthy, especially when it's just purely money involved. You do set up, your trust networks, but especially if you're setting up a company and you're the boss, you make sure everybody owns something, because then they actually have ownership, and they don't think, well, I don't like this job, I quit. No, they're part of the company, so they want to make it better. They think they have access because they're the owner of the company or part owner of the company. So that's to me almost a requirement for new companies. When new companies come up to me, I ask them about their ownership. Hey, do these people own it? I hope so, because I'd rather do business with the smart engineer owners, not some Wall Street guy that owned this company, and all these guys are. I think I had on a previous chart, I had something like being a serf or something. The other big thing that I just kind of want to work on, there's a lot of people have ego problems. Do it my way or the highway kind of thing. Or, hey, it's because I said so type aspect. We don't have a lot of room for that. This is all peer-reviewed type work. It's okay to have a strong ego, but don't let it get in the way of making good decisions. The other one, nobody knows how to do this very well. On the last one, certainly got to hire well, but you also have to be able to fire well. I've been fortunate enough not to have to do that hardly at all. But when you do, we're human. We're all human. Even the person that you're firing, she might have been really bad, really prick, did something illegal. It doesn't matter. They're still human. You need to fire them well, with respect. And people I don't know if business schools actually talk about that, but it happens in industry. So you should talk to your business professors, like, how do you maintain staff and how do you get rid of staff? The other one, I do a system engineering class, and I normally start with this chart. It's a big balancing act for all the subsystems, what you do and why. Ball Aerospace will balance out a system differently than Lockheed would, than Orbital Science would, than I would. But it needs to balance out, and it needs to be reasonably stable. But the far right lower corner, that balances it all out. The talent, time, and money. If you don't have the talent, and that's why it's starred, if you don't have the talent to balance this out, it doesn't matter how much time and money you have. That's coming back to being relevant, being smart, being that you might be smarter than your boss. No one person can do any of this stuff. We generally, when you're doing a science design mission, it's at least 20 people for 20 months to be able to even come to a balance. Talent, time, and money. Talent's more important than anything else. The other applications, I'm going to run through these really quick. This GPS radio occultation, your physics 101, you're passing any kind of a wave through a different medium, a density medium, it's got to get refracted. We do that with GPS signals from space. The GPS signals will hit the atmosphere, get bent by the atmosphere, and back out to space. So we're measuring refracted angles. So this is kind of the picture of it. We're able to back out temperature, density, pressures at higher fidelity than weather balloons do in situ. And we actually go up higher and measure the ionosphere. Why would we want to do this? Well, we're trying to get better isobars, weather forecasting, a thermometer for the planet for climate research. It costs a lot of money from all the damages that we do have. This is a quick example. On the left was an actual storm. We tried to do the forecast on the far right with all the data that you have except for a really reliable temperature and density and water content. You miss it. You're 5 days out or 4 days out and you miss the genus of the storm altogether. When you have some better initial conditions that things like GPS radio occultations give you, you can predict a storm X number of days out. So on the commercial side, we're trying to get all focused on how do we get a better finite element model of this planet so we can have a much better forecast models. And, this is what it would look like with 12 spacecraft and the different samplings that we're able to get from the high stable GPS frequencies going through the planet. So I encourage you guys to look at GPS radio occultation, what a mission called Cosmic's doing. Planet IQ is a new start that we're a little bit involved in, that we'll also be hiring by the time you're graduating. We're doing something very similar instrument, but it's 183 gigahertz. It's a water absorption band, so measuring the exact amount of water content in the atmosphere is extremely important for the next step function of being able to predict what the weather is going to be. We get some water content in GPS radio occultation, but those wavelengths are about this big, and at 183 gigahertz we're able to see so much more water. The next step for the 183 gigahertz one is actually flying it on 2 aircraft. Right now we've been doing mountaintop to mountaintop, some right down here in Tucson. Right now those instruments up are in Colorado with the Laboratory for Atmospheric Space Physics at CU, and we're going to do another mountaintop test here in the summer. Again, you need to be the reason why we're flying in space to begin with. Go find out those ideas in science. And just real quick, I have some kind of crazy people that try to violate the laws of science, and it's very annoying for me to hear that. So certainly if you want work done, you got to move heat. F equals ma, it's been that way for a long time. Hopefully it's not going to change anytime soon. And when you do talk to scientists, you ought to better know your first principles. So you don't want to have them look at you and say, well, if you don't know F equals ma, what else do you don't know? So they're just going to push you out the door. The other just quick parting shots is, hey, there's a lot of fun books out there to read, both on the business side and the science side. I've enjoyed a lot of the Richard Feynman books. He's hilarious. Probably not quite as funny as your guest last night, Bill Nye the Science Guy. I was going to make fun of this guy with a bow tie. I actually brought some bow ties in. I said, well, I'm not going to wear mine this morning, but I probably should have, since you're wearing one. I used to work in D.C. and had bow ties all the time. And I have one little story I probably shouldn't tell you, but I'm going to tell you anyway. I was in an elevator at the U.S. Capitol, and this older guy, probably as old as I am right now, had a bow tie tied up, and I was going right into him. I walked in the elevator, had a bow tied, and he kind of looking down, make sure it was a real bow tie tied. And he just kind of went back up and says, "Good." And I said, "Well, good what?" And he said, "Well, just want to make sure that you tied it yourself. A clip-on tie is like a padded bra. It gives you a false facade." So, okay. So, hope that's a real tie. All right, good. Okay, that's me and my name. You could contact me. We are actually really hiring people. Some down here in Arizona, just up the road, 101 in Broadway in Tempe, the east side of Tempe. Certainly we're hiring people out of Golden, Colorado. We're right downtown. So a lot of you guys aren't 21 yet, but the feature of our location is there's 4 breweries within 2 blocks of our office. So that's a good thing. Like I said, I still like to have fun. Except for that one last beer last night was a little bit too much. We are hiring. There's a guy local here, is Chris Hodge and Kent Narveson, that if you wanted to get interns for this coming up summer, you should contact him. I should have had his email there, but if you just email me, if you're interested on interns in Colorado, Arizona, California, Ireland, Netherlands, whatever. It's probably more local. We don't normally ship students too far away. The other thing is we have desires and wants to expand our missions and payloads and science endeavors, and most of that's in Colorado. So that's what I got. I got some time for questions, I hope. So if you can, and I'll be here all day, so you can talk to me whenever you'd like to.
Does anybody have questions?
He's on. Just in general, any flight computer, spacecraft computer, it's not that dissimilar to normal ones. They just go slower. We do a lot of real-time constructs in the board-to-board package, operating system. Make sure that everything is done within the fractions of milliseconds that it has to be done. So it's more of a real-time, embedded real-time systems for the software side. For the hardware side, it's still mostly PowerPCs chips. Sometimes they're ARMs. We do mostly PowerPCs, 440 bays with a floating point unit, L2 cache, a bunch of memory controllers, and we build that on a radiation hard process. That's one of the things that makes it slower. So we're going maybe 100 or 133 megahertz, which is huge. And you might have 200 megaflops worth of processing power. But for most spacecraft that, I just need to be stable, you're only using 1 megaflop. So you got 200%, 200 times margin. But it's very, very similar. There's a lot of database driven, a lot of MATLAB tools to do attitude control systems, database driven telemetry and control type stuff. Are you a MATLAB person? Okay. All right, well, we'll hire her then, or so get the MATLAB type stuff. No, it's reasonably standard. It's just real time. We just need to really know that it's real time, because everything's clock based.